Hello, I'm Shaun Stevens, Head of School of Mathematics at UEA. Thank you for taking part in our challenge. I'm now going to show you the solution. So the challenge was a cryptography challenge using the public key crypto system RSA. And you were given the public key, which was made up of these two numbers. So this one, which is about 81 billion and 65,537. And a 64-letter alphabet encoded as shown. And the task was to decrypt the ciphertext message, which was written here. So 0, uppercase G, uppercase R, lowercase j, lowercase y, and so on. Right, so the first stage in decrypting is to work out the private key. So we know the public key, we need to work out the private key. So the public key is made up of these two numbers, so we call them n and e. And the first thing that we have to do is we have to factorize the number n, this 81 billion. Now that's quite a big number, but Wolfram Alpha will do this for us. So we just type in factorize and 81027461, and it should quite quickly give us the two prime factors 2521 and 32141. So now we've factorized our number n, so we can write it as a product of these two prime numbers, 2521 and 32141. So now we work out the auxiliary number, which we call m, which is just one less than these two numbers multiplied together. Again, you can use a calculator or Wolfram Alpha to do this, and here's the answer. It's 80 billion and a bit. Okay. And finally, the last bit that we need to do is we need to compute this number, which is called the inverse of E modulo m. So E is this 65537, and m is this number we've just found out. So again, Wolfram Alpha will do that for us. So we type inverse of 65537 mod 80992 and again Wolfram Alpha will give it to us, and here it is, 25,034,273. Okay, so we go back, that's our number, which is this number called the inverse, and so here we have it, this is our D, and now the private key is just the pair of numbers, the same n that we had at the beginning, and this new number D that we've just computed. So there they are, n and D. Okay, so now that we've found the private key, decryption is just the same process as encryption. So what do? The first thing we need to do is we need to encode our message back into numbers. So, and the first thing we need to do is to break it up into blocks. So how big are the blocks? Well, the alphabet had 64 letters, and our number was roughly 81 million. And so we look at the powers of 64. 64 to the power 4 is roughly 16 million. 64 to the 5 is roughly a billion. So this is between 64 to the 4 and 64 to the 5. So that meant that our original message, when it was cut into blocks, they were blocks of 4 letters. And that means that the ciphertext message is cut into blocks of 5 letters. So we cut it up into blocks of 5 letters, and we end up with these 4 blocks. Okay, so now we remember that we need to convert these into numbers. So we have our alphabet here, and we just go through and convert them into numbers. So 0 is easy, that one's 0. Uppercase G is over here, that's 17. Uppercase R is 28, and so on. And we do this for all the numbers, and we get these strings of numbers here. So now we've converted our blocks of text into numbers. Now we have to remember what these numbers actually mean. So these numbers are actually numbers in base 64. So to convert them in from just a string of numbers into a decimal number, remembering this in base 64, the easiest way is again to use Wolfram Alpha. So there is a nice command to do this. It's called from digits. And so we put in the digits that we had. So the first block, for example, was 0, 17, 28, 46, 61. And now we also tell it that we were in base 64. And so that's the command, and we should get this number here. Here's the result, so 4,574,141. Okay, so that's that block. We do the same for all the other blocks as well. And here are all the numbers that we get. So these are our encrypted blocks now, just as decimal numbers. Okay, and now what we do is we do the actual decryption. Okay, and this is where the private key comes in. And what we do is we take each of these numbers and we raise it to the power d. This was this extra number we computed, so this one, about 25 million. And we look at that modulo n, this 81 million. Okay, so again, these are very big calculations. We use Wolfram Alpha to do them for us. So we'll do that first one. So we take the first number, first block was 4574141. We raise it to the power, so it was 25,034,273, and we look at that modulo n, which was 81027,461. And Wolfram Alpha tells us the answer here, 7,814,444. Okay, so again, we do the same for all the other blocks. And what we find, so we do this for all the blocks and we get these four numbers. And so now our decrypted blocks are these four numbers. We have our four decrypted blocks. So now what we need to do is now we need to go backwards. We need to take these decimal numbers, we need to put them back into base 64 and then put those back into our alphabet. So the first thing is to put them back into base 64. Again, Wolfram Alpha has a nice command for doing that. So, and the command is called integer digits. Integer digits. And so, for example, our first block was 7814444, and we want that in base 64. And it should give us a string now this time of 4 digits, 29, 51, 52, 44. And again, we do the same for all of our blocks. And we get here all these strings of digits, now only 4 digits. Okay, so then we take our strings of numbers and we need to put them back into letters using our alphabet. So for example, 29 is the first one, so 29 is an uppercase S. Then 51 is a lowercase o, 52 is a lowercase p, and so on until we get all our letters here. So putting that all together, we see that our final message is Sophie Germain. So Sophie Germain was a mathematician at the beginning of the 19th century in Paris. She's particularly well known for her work on Fermat's last theorem. You can read much more about her online. I hope you enjoyed solving the maths challenge. If you have any further questions about any of this or anything else, please feel free to contact us at maths.challenge@uea.ac.uk.